Okay, so this problem explains that a proton is released from rest at the positive plate of a parallel plate capacitor, and it crosses the capacitor and reaches the negative plate with a speed of 48,000 meters per second. And part A is asking us, what will the final speed of electron released from rest at the negative plate? What's that speed going to be? So you can see here I drew my picture. The proton is going to be released from the positive side and the electron from the negative, and then of course our electric field always points towards the negative side. Anytime we have protons and electrons, we just immediately have a lot of information. But what we don't know right now is the velocity of the electron. That's what we're trying to solve. And then E, the electric field, tends to be part of these equations, so it's notable that we don't have E. And we also don't know the distance between the parallel plate capacitors, which is going to play a role. So in terms of solving for velocity, we want to come up with an equation that includes that velocity term. So we can use our law of conservation of mechanical energy, which basically states that in a isolated system, kinetic energy plus electric potential energy equals 0. So what we can do is just put kinetic energy and electric potential equal to each other and see if we have enough to solve for any helpful values to get to our end goal. So when you keep in mind that electric potential energy is QES plus U naught, and U naught tends to be 0, that initial electric potential energy. We can put that pretty much whatever you want. So just looking at what we have, you can kind of see that we have enough to solve for the electric field, which is going to be very helpful because the electric field in a parallel plate capacitor is completely non-related to the charges inside of it. So that electric field is going to be useful in an equation that if we're looking at an electron, just as it will with a proton. Same with S, that distance between the parallel plate capacitors, which is also going to be useful. So you can see once we rearrange our equation, the 1/2 mv squared equals QES to solve for E, we get E equals m times v squared over 2QS. And so all you have to do is plug in your values, and you get E equals 12.02 over S. And so I went ahead and just said ES equals 12.02. And once again, what's going to be really useful about this is E and S are both going to be the same, whether it's an electron or a proton. So we can apply this number to our equation where we're going to be looking at the velocity of the electron. So moving on to that, once again, we're going to be using that mechanical energy concept where we can set the kinetic energy equal to the electric potential energy. But now we're solving for the velocity. So we get that the velocity of the electron is square root 2QES over ME, that mass of the electron. So yay, we have ES right in the equation where we can substitute really easily. And we do have the other values, Q and ME. So all we have to do is plug things in, plugging in 12.02 for that ES part of the equation. And we get a velocity of the electron of 2.1 times 10 to the 6 meters per second, which I think I calculated it, and it's something like 40 times faster than the proton. So incredibly fast for an electron in this parallel plate capacitor. So this problem can be a little bit tricky to figure out how to connect the equations, to figure out how to solve for ES as a whole in the proton equation and apply that to the electron equation. But once you do that, I think it's pretty simple. Also, just always remembering there's the general concepts. The law of conservation of mechanical energy is going to be really helpful for this. But yeah, overall, not too bad. Thank you for listening.